Let's find out how many different hydrogen there. If you remember that, we kind of classify them by the degree of substitution, right? How many carbon substituents it has. So first of all, there is a hydrogen on this carbon, and we call this a primary hydrogen because this carbon has only one carbon substituents. Same thing for this one, same thing for that one, right? So all of these hydrogens are something we can call primary hydrogens. And there are many. So read from here to here to here. So 909 primary hydrogens. And then we got hydrogen on this position, right? That is a we call secondary hydrogen because this carbon has two carbon substituents. There's one more. There's a hydrogen right there. And that is something we call tertiary hydrogen because this carbon has three carbon substituents. So we classify them by how many carbon substituents on each carbon, right? Because those hydrogens going to be pulled out by the bromine radical, and then radical is going to be formed on those carbon. So stability of the primary carbon, secondary carbon, tertiary carbon. So that's why we classify them by the degree of substitutions. Anyway, so it's going through that. Remember that this is a radical reaction, so we are supposed to use a half arrow, right? Not the full arrow, but it's a single electron being. So one electron is going to be given, and then one electron is going to come, so they're going to make a bond, and then the one electron is going to go to the carbon. That's why it makes a carbon radical at the primary carbon. If you pull out the secondary carbon, then you definitely going to put the radicals on the secondary carbon, right? Same thing goes to this position. If the bromine radical comes and take out the hydrogen and tertiary carbon, then you're going to form the tertiary radical. So all three of them will be formed, and then they will go through the second propagation step, which is this radical pick up the bromine from the bromine molecule, then you get to form the bromine at the carbon. And then this secondary carbon will put the bromine on the second that position, right? And then this tertiary radical will make a bromine on the tertiary carbon. So those things going to happen. I don't know which one's going to be the major. I just write down this. All of these things will happen. Then we need to think about which one's going to be the major product. Potentially, this could be the answer, that could be the answer, this could be the answer. We see all the possibility. Now we need to know, we need to say which one is going to be most likely. That has to do with the stability of the radical. As we mentioned earlier, the more stable intermediates will form more. And because of that, more products coming out from the more stable intermediates. And then the stability of the radical depends on how many carbon substituents it has. The reason is the radical is an electron deficient species, and then the carbon substituents can help them. Primary radical has only the one carbon substituent, so one guy helping it out. But secondary radical got the two carbon helping it out, so secondary radical is the most stable than the primary radical. But now there's a tertiary one, right? Three carbon chains donating electron density to the radical is being the best of the three. So which one is the most stable radical? Tertiary radical. And then because the tertiary radical being more stable, that's produced this bromine sitting on the tertiary position as a major product. So this is how you're going to solve it out. Organic chemistry, in my opinion, is almost like a math of the life sciences. You're not dealing the numbers, addition, subtraction, division, or any of those things. But the way you approach to the solving organic chemistry question is the same way. You have to drive it, you have to work it out. You just cannot guess what it is by the time you study the biology. Some people are really good at studying biology because they have an infinite amount of capacity of memorizing everything. You can work it out that way, but chemistry, if you do it that way, just like you do memorizing how to do the trigonometry. I mean, in some sense, we could work it out, but if you really get into the difficult question of trigonometry, memorizing sine theta is what doesn't really help you because you got to know how to apply it, right? So organic chemistry is almost like that. So if you're good at memorization and not good at solving it out, then you got to try hard to make yourself get better at it. If they're trying to memorize how to solve organic chemistry question, it could work up to some point, and then but you're not going to pass that. That's the problem. I'm never going to say that you will fail. It's just that we always lay a trap for those students who just memorize everything. I mean, being able to memorize a lot is helpful in the end, but it's not going to solve the problem today, especially for subjects like mathematics and organic chemistry. So that's kind of an unfortunate reality. My suggestion is solve it out. You got to draw it up with an arrow. What goes where? Well, how electrons are flying this way, that way? What is getting formed as intermediate? How they mix the products? How many steps it needed? You just have to do it all through it. That's the kind of things you want to get used to it. All right. Second one. Now you see how the first one is being solved. So it's kind of not a very different one. You just have to do it in different molecules, right? That's what it is. Same reaction, we got the bromine and lights there. So it's clearly the radical reactions. The bromine radical is formed by driving the light to the bromine. So that is a free radical chain reactions. And that is going to be start abstracting hydrogen from this molecule, but it's not the same as that. So now we're going to approach it a little bit differently, but the concept being the same. Let's find out which hydrogens are there, right? First thing is, yeah, there's a hydrogen at this end position, but that's a primary hydrogen, as we said. That's probably not going to be the ones, right? Because once those goes out, it's going to make a primary radical, which is not good. Then are there secondary position? So that's kind of what you need to look for. Are there any different types of hydrogen there? And yes, there are hydrogen in the secondary carbon. This carbon is a two carbon substitution. So that's a secondary position. So there's a secondary hydrogen there. And then there's a one more secondary hydrogen. If you remember that, this hydrogen right there, that has a 2 carbon substitution. So that's also if you make a secondary hydrogen. But this is a mistake that you're probably going to make it. The hydrogen on double bonds, right? This is a hydrogen directly bound to sp2 carbon, part of double bonds. That is not the subject of the free radical chain reaction. Because of these hydrogen carbon, sp2 hydrogen carbon bonds are both stronger than the hydrogen and the sp3 hydrogen carbon. Breaking this one out is not as easy as breaking the others. So hydrogen on double bonds doesn't participate in this free radical chain reactions. Right? So don't even consider that. So not this hydrogen is going to be the issue, nor that one. Not only the reaction chapter 4, even the reaction chapter 6, the most difficult chapters, you see the hydrogen on double bonds never going to be subject of the reaction. It will be later, but until we pass this second test. So don't try to use any of these hydrogens or halogens on the second the sp2 hydrogen part. Anyway, I'll give you the one later once we see another part, but this is not the things. And then there will be tertiary hydrogen right there. This is the 1, 2, 3 carbons surrounding it. Carbon. So this is a tertiary carbon. So we got primary, secondary, tertiary hydrogen there. So what we can do, let's find out what radical those things will form. So start with the primary one. If this hydrogen is pulled out by the bromine, this carbon is going to be left with a radical. Those formation step, if you remember that. The secondary hydrogen, if the bromine comes and take it out, that's going to create a radical at the secondary carbon. All right. And then the tertiary carbon, if you take one out, the radical goes right there. And the primary carbon and secondary carbon, tertiary carbon, probably tertiary will be the best because they got the most carbon substitutions. But in this particular case, not only that, but also these ones are more stabilized. Can you guess what the extra factor for stabilizing that tertiary radical? It doesn't have this one doesn't have that one doesn't have that, but this one has. So what is it? Yeah, that's a resonance stabilization. So that's the reason. The first thing we learned about resonance stabilization, inductive effects, stabilizing of the anion, whatever, the same concept that applies even other things, all the way through the end of organic chemistry. The things that we learn you just cannot forget. You just have to constantly apply them, even though those things are not mentioned. But anyway, so these tertiary radical, not only being a tertiary, that is already good, but this double bond next to that is stabilizing, it is a structure, so you get extra stable tertiary radical. So which one is going to be the product? Yeah, the primary radical can take the bromine, produce that. Secondary radical can produce this, but that's going to be really high. Most major form is going to be this radical, pull out the hydrogen, I mean the bromine, and then put the bromine there. So that is an answer you probably like to get. And then I'm going to say, yeah, you only half right. Why is that? I mean, you done everything right? Just remember that these tertiary radicals form, this one pick up the bromine, you put the bromine there. So where the hydrogen is, you just have to switch the hydrogen to the bromine. That's the answer. So what is wrong with this? This has to be right. And I'm not saying that you're wrong, it's just the half of what it is. So which the other half is answers are in the resonance structures. If you look at that, these radicals in this position on this resonance form, when these double bonds move out here, the radical goes to the other carbon as well. And these things are about 50-50. So 50% radical characteristics are on this carbon, which will produce that. But another 50% radical characteristic of the other carbon, and that is also going to pull out the bromine and then producing other major product. So we are expecting two major products in these reactions. Not one, but two. It's all because we got two resonance structures, and then the radical characteristics are here and there, about 50-50.